So we have Dave Richwine, who I bet a lot of people here. And we have a certain, if you did, Olaf, you probably didn't hear it, but his expression was quote unquote, oh God, because he thought I was going to introduce him, because we usually try to have somebody who knows the person to introduce them, and who I am not the person to introduce Dave Richwine, but the wonderful Lil Richwine knows him far better than I will ever know Dave Richwine. So, Lil, it's up to you.
Okay. It truly is an honor to introduce Dave. I've never had the pleasure of doing this before, and I had a different speech ready, and then I went online and read his bio, so I think I better stick with the bio. Okay, so Dave Richwine serves as the Quest Mission Integration Lead and Low Boom Flight Demonstrator Deputy Program Manager for Technology, coordinating technical requirements and capabilities across the mission. Dave received his mechanical engineering degree from UVA in 1983 and his master's from George Washington University in 1986. He worked in aeronautics research for a combined 40 years at Langley and Dryden. During his 17 years at Dryden, he met me, got married, had kids, but he also found time to work on several research projects, including the F-18 High Alpha Research Program and the F-15B Flight Research Testbed. And he served as Dryden's project manager for DARPA's Quiet Supersonics program and the F-5E flight test. After moving to Langley in 2003 to be closer to family, he served in several positions supporting NASA Supersonics research. In 2012, Dave was the planning lead for and then managed the low boom flight demonstrator concept studies, which ultimately evolved into the X-59 aircraft preliminary design, LBFD project, and now Quest. So, let me welcome Dave to the platform.
That was a little weird, wasn't it? At least he didn't make up any stories that could have happened. All right. Well, welcome everybody. I want to thanks. Hopefully I can make this fun. So I got to. Does that one have to be off? Yep. Okay. So I got a call from Dave Hinton, I don't know, about 6 months ago, and wanted to know if I wanted to give a talk. And I was like, sure, no problem. That sounds interesting. I think Dave was kind of expecting me to do X-59, but my real plan, I'm probably going to wander. Is that okay? My real plan was to give a little talk that I had some history on, where about a year and a half ago, I was asked to put a timeline together for the hangar where we're going to put X-59 out at Armstrong. And so it was a long timeline, and they want to talk about the 80 years of supersonic research. Funny, when Dom and I were 60, now it's 80, huh? It's getting close, right? It's hard to believe. But anyway, so we had this timeline, and it just turned out to be a real interesting little timeline. And I thought, hey, well, let's just turn it into a pitch, add some more material. Last summer, I presented it at Oshkosh, and then later I presented a kind of variant of it to the docents up at the Air and Space Museum, and they found it real interesting. So I kind of thought it might be something kind of fun to do for this crowd, and not too technical, but lots of fun pictures over the last 80 years. So here it is. I want to thank all the contributors that have worked on this. Again, Dom, Peter Cohen worked on it, had Dr. Gelser, who's a historian there, and various other folks, and also all the folks that really worked on these programs over the last 80 years, and now on X-59 as well. It's been a great team to work with. So when I do the dates here, it's going to be the dates of the NASA research, not so much the dates. So you're going to find a lot of these airplanes. Am I? Oh, block. Okay. See, I'm not doing it right. Okay. Yeah. Okay. So what you're going to find is a lot of times these airplanes were used for military purposes, but there's a little slightly different date when the NASA research was done on these airplanes. So this is a picture of taken a couple years ago of two T-38s from the top view using synthetic Schlieren now, which is a kind of variant of Schlieren that Leonard Weinstein did on the T-38, I don't know, about 20 years ago. And it's really, you can see now the technology has really increased on this. So it's a really sharp picture now that we can see this is an actual flight vehicles, two of them in flight, and you can see the interactions of the two airplanes in formation. So let me move on. I did this pitch in about 45 minutes. I'm going to try to do it pretty quick. I did it at Oshkosh, it took a little longer, but I'll try to move along pretty quick. Am I holding it right? Okay, all right. So I think we all recognize that dapper young man there, Chuck Yeager, right? We all remember Chuck Yeager, but it was actually, there was a lot of other pilots that flew this airplane, but he's the most famous. I think some of you guys, depending on your generation, remember him as the Delco battery guy, right? I think he was in those commercials in the 80s or something. But he flew in 46. They started flying the airplane, and then he went supersonic. I think it was Mach 1.06, and there was a lot of debate as to whether the boom reached the ground or not. But anyway, it was kind of the beginning of the X-plane era, right? So the X1 primarily was to show that we could break that sound barrier. I know it all kind of sounds funny to us today, but in those days they weren't sure if they could fly faster than the speed of sound, right? And so, and really also look at the aerodynamic viability of those very thin wing sections. When I look at this airplane, sometimes I'm just like, my God, that wing was so thin. It's just hard to believe that the structural guys could make that work. But anyway, that was the beginning of the X-plane era. Then we got to the X1E. They found they needed a little, kind of tweak the airplane a little bit, make it a little bigger, new propulsion systems, and they wanted to get up to Mach 2.2. And so again, they're looking at the directional stability, used different fuel, swept the wings, a couple other changes, and again, NASA went on and did more research in the mid 50s. That airplane now is out at front at Armstrong in Building 4800, and I don't remember. Have some of you been out to Armstrong? That's the I Dream of Jeannie kind of shot, in front of that building there. If it looks familiar, all that wonderful vegetation out there. Well, I got another picture later. Yeah. So here's another one with the F-104. I wanted to show this picture. I think if I remember right, so you have to bear with me. Some of these are my favorite pictures, so you had to like shoehorn them in. I think this is the last flight of 826, which was flown by Tom McMurtry. And I just thought it was kind of a great shot. But the F-104s were just a real, they were the support airplanes, 38 years, 18,000 flight hours. In a research environment, that's a lot of flight hours. And they flew all kinds of missions. And the 104 was the first airplane to measure or probe that near field shock during supersonic flight. So that was kind of the first step into understanding the near field aspects of the sonic boom, not just measuring them on the ground as well. And this is, again, one of my favorite pictures of the 104 doing rain erosion studies. So there was a period, I think it was in the 80s, where they did a lot of rain erosion, 70s for the space shuttle. And they've got a Nolenberg probe out on that right wing, and they would go fly through rain and look at how the shuttle tiles were eroding. So a lot of as the evolution of the tiles occurred due to some of the research they'd done here and in other tunnels. So that's kind of a real interesting picture. Makes you realize that the 104 was kind of like a lawn dart, right? And just like our 69, right? Okay, so X-15. Again, this was not a supersonic airplane, but you certainly have to get there. This was a hypersonic research airplane, used a lot for, everybody kind of knows it went Mach 6.7, very high altitude, did a lot of space flight work, but also it was kind of the beginning of our understanding the sonic booms, and particularly if they could have gotten a better picture. You can imagine flying chase on this airplane was kind of a tough task, but if you could have seen that plume, it was very large. And so it was the first time you could see that the overall plume and how it might have impacted the signature of the airplane on the ground. So it was the first time that they learned that, oh yes, the plume of the airplane can also impact the sonic boom. And I just thought this was kind of interesting picture. I was fortunate enough to work with Milt Thompson and Bill Dana. I think Pete Knight was the mayor of Palmdale when I was out there, but just kind of interesting that just imagine those guys and the dedication to wear that outfit going flying. I mean, that was a interesting group. And then Neil Armstrong over there too. So then we the Century series airplanes, And the F-100, the Super Sabre, was really the first of those. And a really interesting group of, there was really the first supersonic fighter, so there was a lot of research done on all of them, but the F-100 was used by NASA for sonic boom research to help with the X-15 and also help with the SST program. And just kind of some real interesting airplanes. And I think, if I remember correctly, I think the F-100 was either the first or the only airplane that was used for the Thunderbirds and the Blue Angels for 2 years. I guess I never knew that when I was doing a little research, that there was actually airplanes that served in for both agencies. The B-58, I have to admit, Dom helped with this a little bit. Was not very familiar with the B-58 until we actually did the book and talked to Dom a little bit about this. But this was a supersonic bomber. It was for its time, very large load carrying capability, quite big, 96 feet. So it's getting up there in length. And it was not the best airplane, but it was the most similar to future supersonic configurations, which tended to be much larger. But it was the first one where they could actually demonstrate the contribution of the aircraft lift on the vehicle. So it wasn't just about the volume of the airplane. It was actually learning that the lift was a major contributor to that near field shock wave and managing the resulting ground boom that was going to the ground. Interesting airplane. You can tell that was just a brute force going supersonic with a big airplane, like a lot of engines and a lot of fuel on that airplane. XB-70, gosh, when I did research on this, you could talk about this as just its own presentation almost. It's really a pretty iconic airplane, quite large, Mach 3 bomber. It was ideal because it was very similar in size to those SST airplanes and all the problems that they had, from the sonic boom to control system design. And there was a lot of studies, again, probing on this airplane as well. One of the things I didn't know about this airplane, I was doing a little research, is that they actually were trying to put a supersonic, so this was going to be a nuclear bomber that was supersonic, but they also were trying to put a nuclear power plant on board this airplane. So I think they spent several years trying to figure out how to put a nuclear power plant, and we know how that goes sometimes. It's pretty complicated to put a nuclear power plant on an airplane, and so it was abandoned at some point due to cost and complexity. But I guess I had never known that they were trying to make this into somehow a supersonic propulsion system that was nuclear capable. And this was also probed by the F-104. So the F-104 has kind of a long history as a probing airplane, but pretty tremendous airplane. When you think about the size and you think about these two guys sitting down there looking at that airplane, that is an enormous airplane. And we also know that there was the unfortunate accident where several pilots were killed with a F-104 mid-air collision. And that was kind of the beginning of the end of the research program. But the airplane was just real interesting, had wing issues, had to increase the dihedral to make it stable. But they learned an awful lot about the very ultra-large supersonic configurations for the future. And this picture here was just before that 104 with the orange tail crashed into the XB-70. And then just wanted to say, if you've ever been to the National Museum of Air Force over in at Dayton and Wright Pat, there's a XB-70 is in there. And underneath the XB-70 is the SR-71. So it really gives you a pretty impressive scale of how large that airplane is. More modern day, we're getting into the 80s now. We had two F-16 XLs. I know Langley worked on some of the XL work. Has anybody in the room actually worked on F-16 XL 1 or 2? Cliff, yeah, you did some laminar flow work on it? Yeah. So there was two of them, an XL1 and XL2. XL1 was looked at some aerodynamic data, and then XL2 was modified to look at laminar flow control, and this is XL2. So the black glove on this airplane is actually a laminar flow control glove, and I think they found out, look, Cliff, I mean, maybe you can tell me, they largely found out they could get laminar flow, but there was so much energy put into it, it was a question of, could you efficiently get laminar flow? Is that about right? Okay. Yeah. So this is 2. And then we have 1 here too, chasing the SR-71. So there was 2 SR-71s at Armstrong in the early 90s, and they were used to look at this as a high-speed platform. and also as a launch vehicle. So as a launch vehicle, they were thinking about launching stuff off the top. They also did some work on a laser, which was the X-33 propulsion system. But the idea here was to probe the airplane and get a database and see if you could get your computational methods lined up with your actual measurements. And XL1, which is, I think at Langley too, I don't know, what did XL1 at Langley actually do? I wasn't familiar with the research. Right. Okay. And so here's, again, it's measuring the shock of the airplane, probing very close to the airplane. So here's the kind of the gang. I think many of you probably know some of these pilots. Marta and Bob Meyer are the two in the middle. Worked with a lot of folks here on the XL program, and so several of you might have worked with them in the past. And then I know Steve Ishmael worked on X-29. That any folks that might have worked on that. And then Rod Smith was kind of an X-31 guy. So anybody who worked on those programs might be familiar with them as well. And Ed Schneider was not in this picture, but he was also a pilot. F-15, 836. This was the first project I ever got to work on at Armstrong, where I was the project manager and the chief engineer. So it was kind of an emotional airplane for me. I just kind of love this airplane. You can look on the back of it, the tail number. You can see this airplane's actually 50 years old this year, and it's still flying. So this is the oldest F-15 in the entire country that is still flying. It's the only B model. I don't think there's even C models flying anymore. But put a lot of experiments on the bottom. This is an example, the little black fin on the bottom. It's real interesting. That was the Arion, kind of an example of the Arion airfoil that they wanted to fly on their configuration. But there's also been propulsion fixtures underneath, different wings, all kinds of different things we've put under the airplane to do a lot of the testing. It's also the F-15 and the nose boom was the probing for the SSB airplane, which I will talk about next. And we're also putting the next shock measurement probe on the F-15 to go test out the acoustic validation for this next phase for LBFD. And if you guys are all familiar with Eagle, Dom and the Eagle guys actually kind of were the inventors of the shock probe, and it's had a slight design changes over the years, but that was designed to be a good measurement tool for in-flight shock measurement. Tu-144, I think all you guys probably remember this airplane. This was kind of what I call the Cold War opportunity for international collaboration for the HSR program. There was 27 flights over about a 2-year period, 3 by NASA pilots. And I gather one of the primary purposes was to get supersonic data, collaborating with the Russians. I think they were also trying to keep the Tupolev engineers busy doing good things instead of bad things. So I think this was a little bit of an employment program at some point, but they did get some data out of it, and that was a good thing. I just thought this is kind of a fun picture. I found this picture here off, this was a cell phone picture off from Gordon Fullerton, who's a pilot out at Armstrong. And then you guys probably all remember Rob Rivers. It's a good story there. Rob was a big hiker, I gather. And I think he was out hiking and he either broke his leg or did some kind of severe leg injury while he was on a hike. And I guess he figured out a way to fly that airplane with a cane. So not really sure it was a safe thing to do, but he was so motivated that Rob figured out how to get on that airplane and fly it. And you could just see how big this airplane is. And it has the nose much like the Concorde, where you have the drooping nose so that the pilot can see on landing. Okay, then we get to the SSBD program, which was a DARPA-sponsored program with NASA, working with Northrop Grumman. The whole idea here was, and let me go back just a second. So I want to make this point. So from 96 all the way through 2003, there wasn't a lot of supersonics flight research being done. So it was a pretty big span of time where we weren't doing a lot of research. And so it was kind of felt like this kind of reinvigorated the supersonics research. SSBD airplane was essentially an F5 with a modified front. It had to be unmodified at some point. So it kind of limited the shaping. So that's why it looked a little bit like a pregnant guppy on the bottom. But that was the whole idea, is to modify it to get that shape and show that that sonic boom could propagate all the way to the ground and be realized. And this was the first time that we really had a sense of that. So it's really, everybody kind of has felt like this is kind of was the vehicle that led to the resurgence of sonic boom research. And this is one of my favorite pictures up here on the left, where they had an F5 and then up against the SSBD airplane, and then the F-15 that was the probing airplane in the air at the same time. And it just turns out that if you can look at the red curve and the blue curve, the blue was SSBD and the baseline F5 was the red curve. And we actually got exactly what we expected to get, which was also painted on the airplane. So there's the proof, is the paint scheme on the airplane was exactly as the data was gotten. And then there was a really brash pilot named Roy Martin, a guy named Joe Pulowski, and I don't, Dom, you may be able to say who actually said. So Joe actually said the statement, I think, but I think Roy was the one that kind of brought it in the pilot's attitude. He felt that, Chuck broke the sound barrier, but we just fixed it. So that was pretty funny. Everybody got a big kick out of that. But that was Roy Martin. If you've known him, he was a pretty brash pilot. And again, but it was critical to us understanding that we could get that sonic boom to the ground and craft it as to make it more into a sonic thump. Back to the F-15, we had another thing where we worked with Gulfstream. Excuse me. The idea there was there was the gentleman at Gulfstream that felt like if we could put a spike in front of the airplane, you essentially create a longer airplane, artificially longer airplane, and you could put this spike in and out. And so Gulfstream really tested this as more of a structural concept than a low boom concept. But it did show that you could do this, and it was a way to make your airplane lower boom if you desired. I think we have learned that probably the weight and the tertiary complexity of this is probably not worth just making yourself a longer nose if you can do it a more of a fixed nose. And that's what you'll see on X-59. And we just went with a longer nose, and you kind of deal with the problems associated with that. F-18s, there's nothing too special about the F-18s. They did a lot of research at Armstrong for many decades as well, and they still have a couple remaining. But the important one here is Ed Herring and several folks designed a supersonic dive maneuver that could really create a way where you could create a localized low boom for flight testing and also for on the ground to kind of understand how to do community tests as we move forward. So this is a picture of the dive. So they would actually go up to 50,000 feet and actually do a 52-degree inverted dive. And what it would do is place a focus boom in the red area where you have a real high sonic boom, but then you have a lower area, a lower amplitude area that you can actually do your community testing in. So it's a way to kind of understand how to do community testing, even though it's a little artificial, and you have to be very careful in the way you manipulate the flight testing. And then here we are on X-59. So I think originally Dave was thinking Dave's going to talk about X-59, but I'm only going to have a couple of charts. I just thought it might be more interesting for you guys to see kind of the history of how we got here moving forward. But really, it's a climax of 75, 80 years of supersonic research and X airplanes since Chuck Yeager. And it's called the Quest mission. And it's really been a great team that I've worked with to get to this point. We hope to create that sonic boom down to a sonic thump. So it might sound like a door closing next door or a heartbeat going by instead of that startling thump that many of you might have heard. And then the Quest mission will use that airplane to do community studies to hopefully get regulatory change and open up that market so that folks in the future can fly supersonic across country, but also do it in a sustainable way that's environmentally friendly as well. So at the same time, while we're doing this airplane, Supersonics is also working some of the technologies to make sure it's clean and efficient as well. Give you a real quick, because I know this is going to get too long here, but timeline right now, first flight is this year. We're hoping by the end of the summer. It's kind of where it's looking right now. As you know, when you build a one-of-a-kind airplane, it's very complicated. Integrated testing is extremely complicated. So that's where we are right now. Second phase, after we go out and prove that the airplane's airworthy, is to go do acoustic validation. So that would be flying around Armstrong and Edwards Air Force Base, probing the airplane like we've talked about before. We have a TG-14 glider where they can fly it, turn off the engine, and get acoustics data. And that helps with getting what I call the turbulent boundary layer effects, like turbulence in the atmosphere also impacts the sonic boom. And then the ground measurements. So once we do that, get comfortable with all of our tools are in place, then we would go fly over communities over the United States and representative communities where we'd get this data and present it to ICAO, which is the international regulatory agency that would control this. What does the airplane look like? I'm not going to go into all these, but generally you have two things you're trying to do with the next airplane is you're trying to meet your technical objective, and then you're also trying to make it cost effective. So an example of your technical objective, a very long nose. So we opted not to go with this complicated articulating nose, just make it very long so that this airplane is quite quiet. Excuse me. We also have the wing and we have the engine on top. You wouldn't want to do this for a commercial product, but for us, it's better to use a standard off-the-shelf engine, put the engine on top so that the aircraft is the boom is insensitive to the different throttle settings. So that's why it's on top. If you had a commercial product, you'd most likely want it on the bottom so it's serviceable. And then we had a conventional engine, F-16 landing gear. So this airplane is kind of a Frankenplane from a cost perspective, probably about 6 or 7 different airplanes. We even have a stick from a F-117 in this airplane. The hydrazine system is from a U-2. Again, the landing gear is from an F-16. The engine is from the Super Hornets. So it's really all over the map. We picked the part that best matches our objective and going forward. And this is about 99 feet. So, roughly the size of a basketball court. So where we were last summer in August 2023, the airplane's built. This is before it was painting. It was out what's called Run Stall 5, where they've actually got fuel in it now. And started doing integrated testing. And then here we are in January this year, where the airplane got painted. And this is my desert picture. So if you always wanted to know what it looked like out at Armstrong, well, actually, this is in Palmdale, that's Skunk Works. All those Joshua trees in the brush, and then all those windmills in the background is because it's usually quite windy out there. So it's a beautiful place to live if you really like the desert. And it's, sometimes I have kids ask me, it's like, well, did you guys design that airplane so it looks cool? And as it may look cool, but it's a little unorthodox as well. But every part of this airplane, from the tip all the way through the tail, has a purpose. And so very carefully crafted airplane to get us that data that we need. This plane has to be quieter than what a commercial product would have to be. So we want to go out and survey data. And so we want to be able to fly over your house and you not even hear it. So in order to get that kind of that noise exposure data that we need to go from not hearing it to being aggravated by that or startled by that sound. So that is about it. Does anybody have any questions? I kind of whipped through that pretty quick. Happy to answer any questions if anybody has any. But that's about it. So Dom, did I get anything wrong? Dom's like, yeah, you got a whole bunch of stuff wrong.
Dave, we do have one question online. This is from Damodar Amber. We know there are technical and regulatory challenges that need to be addressed before launching supersonic civil transport. One challenge is emissions, with progress being made on alternate fuel and hybrid propulsion systems. Can you share any information on the approach FAA is taking on developing requirements for emissions?
Yeah, I can't really comment on the FAA particularly. I guess I'll comment on the NASA. They always tell you don't comment on other organizations. But so this airplane can take alternate fuels. So when we designed this airplane, it can take some of the SAFs that are being used. Really, right now, the purpose of this airplane is to work the sonic boom challenge. The CST project that Lori Ozorowski manages, they look at all the different efficiencies, noise, sustainable fuels, all those kinds of things to make sure this airplane can be sustainable. But we're kind of focused on sonic boom. That being said, we did design this airplane so that at some point in time, someone said, hey, can you go fly a couple missions or fly a whole deployment with alternate fuels? We can do that. Or they would want to survey us. This airplane would be pretty hard to survey because we typically fly about 55,000 feet on cruise. So it would be very, very difficult for them to survey the pollutants, that are coming out of this airplane. But we are very aware of that challenge, and there are other people that are working the sustainability part.
All right, thank you. We do have two more questions online. The next one is from Olaf. What do you see as a follow-on 10 years from now?
Well, so it's going to take, we're probably going to be flying this airplane through 27, 28 to get that community response data. So there's many years of flying. Post X-59, we probably have a lot of research that could be done on this airplane, but that's something that headquarters would have to decide. We're also competing against X-66, which is the truss brace wing, the subsonics, and AAM type work. So there's a lot of competing budgets and technical work. But I think one thing for sure is that we have to continue our sustainability part, looking at noise and emissions of these airplanes, because we may get the sonic boom hammered out, but at the same time, we really got to work all that sustainability issues to make this a good product going forward for commercial purposes.
I seem to recall back in the dark ages, some of my colleagues who were working on the sonic boom saying that the area under the pressure wave was proportional to the lift on the airplane.
Right.
You really couldn't change that area. All you could do is change the peaks and valleys. Is that correct, or is this just a faulty memory of an old man?
Well, I think we have a little better understanding of that now, but certainly the lift combined with the volume distribution, also combined with the length of the airplane, and it's not just the magnitude, but it's also the rate at which you hear that magnitude. So it's like you get a traditional N wave, it becomes more startling than if you get a more of a shape signature. So it's a little more complicated than that, but that is a factor, is the weight.
Yeah, Bill, I know there was a lot of prediction and design work done to come up with the shape that we're flying in X-59. And I know that there was talk about probably the first integrated operational airplanes will probably be corporate jets or smaller airplanes.
Right.
Probably not full commercial. Are there any conceptual studies being done by industry using the results that we've generated so far?
Yeah, so we've done they call them N+2, N+3 type commercial studies that the typical companies will do, like Lockheed's and the Boeing's, looking at all the technologies that need to bring forward. This just happens to be the first one, right, which is that sonic boom challenge. But again, there's many others that have to do with sustainability, maintainability, cost, and so on. So there is work being done. I know that there's also Hypersonics is coming up with a Vision Mach 3 Vision vehicle that is really supersonic, but it's more of a hypersonic. They view it as a hypersonic configuration, and they're looking at the type of technologies they would need for that as well. And then there's the people like Boom that are trying to fly right now with their demonstrator. I think they had their first flight 2 or 3 weeks ago, where they're just trying to show that they can fly kind of more of that business jet model that you're talking about, just flying across the country. It's important for us. We want to achieve overland supersonic flight eventually, where a Boom is more interested in the jet model that you're talking about.
Okay, thanks.
Chuck Bivik asks, can you describe the technical approach for controlling the boom?
Technical approach. Okay. Well, I don't want to give you a lecture. So you're really trying to balance two things when you design the vehicle. Is you want to carefully balance the volume distribution in the airplane and also the lift distribution at the same time. So the front is really largely dominated by that volume distribution and how you shape the airplane. Again, much the reason why we have our canopy and cockpit area, it doesn't have a big bulb, for example, and we're using external vision for our forward visibility. So it's, again, you want a smooth distribution. In the back, it gets very complicated. It gets dominated by the lifting surfaces and the very complex interaction of the lifting surfaces. So, for example, the T-tail in the back is actually managing. So we're also managing along the Mach line, not along the cross section. So for the T-tail, you're actually managing aft of the airplane. You're managing the sonic boom and the shocks coming off the inlet. I mean the nozzle area. So it's just a very complex from tip to tip, making sure that design is a smooth design, both aerodynamically in the lift and also that volume distribution. Hopefully I got enough details. I don't want to give a sonic boom design 101. So there's guys that do this all day long, and it's quite interesting. You know, the one thing that's enabled this is the CFD guys these days. And it used to be in our sonic boom book, you know, like Christine Darden and so on, you know, they would all get all excited when they had 1,000 grid points on their CFD model. Well, now these guys are talking like 80 million points and just crazy numbers, and are able to do that pretty effectively. And so an airplane like this really requires that very high resolution computational work. And also a lot of wind tunnel testing to verify that.
This is Dick Hushin, and I had a question. Who developed the technology to land this airplane without any windows to see?
So that's a great question. I don't know that they've invented the technology, but Randy Bailey and the branch here, their group did a lot of work on synthetic vision, which is really synthetic is an electronic map of the country, and using synthetic version in Gulf Streams probably 10 years ago here at Langley. So the Langley folks, the team here in the D318 branch, designed the XVS system that is in the airplane right now. It has synthetic vision, but only as a backup. So we actually have external vision, which there's a camera on top. It's a high definition system. So it's almost better visibility than your eye would have at this point. And then there's a forward vision system that drops down when you're going subsonic that helps you see the land. And so what Randy's team did is it's all computational now. They sew the images together. They put an ADS-B on there so you can see the cooperative traffic. There's a HUD on it. So it's just a huge amount of information that pilot has now. Without that natural forward visibility, he's got that external vision system to rely on. Okay, Dom's going to give me a really hard one that he knows, and I don't.
I think one of the most significant things about this, about the X-59 is it does not produce the N wave. Every airplane that has gone supersonic so far, with the exception of the Supersonic demonstrator, in the far field, you always got an N wave at the ground, which was a boom boom. This is tending toward a sinusoidal wave, which is a softer boom. So that's the key to it.
Right. And so the challenge that we're having is the front is relatively straightforward on how to manage that. The back gets very complicated with all the lifting surfaces and the moving. So even stabilator position changes on this airplane can force that pressure wave back into an N wave. So we have to figure out how to manage that so that it's more of a sinusoidal shape than that N wave that would give you that high boom. Peter Cohen's in the room now. You can ask a hard question.
Great.
Okay. If you got any really hard questions from the last like 40 years, Peter can answer them. And you want Dom from eternity, Dom can answer them, right? In fact, I think I was going to ask people to raise their hand when they worked on projects, but I figured Dom was just going to raise his hand on everything except for X1, right? So that wouldn't have been fair. So we are not looking at engine noise. That's why we're using an off-the-shelf engine. This engine will be an afterburner when we're on cruise. And we're not doing any kind of airport noise type work either. So no, this is not an airport noise type research experiment. This was started in the Dr. Shin days, and Dr. Shin was always like, you manage to work one technical challenge at a time. Don't try to work so many that you can't get them done. But that work is being done over in the CST project and by others. So Tony's a structures guy, and so we have a lot of structures problems on here, both aeroelastic and static structures problems, right? This is definitely an aeroelastic problem. So again, these are disciplines we need to tap into to fly safely, but it's not research that we're doing necessarily. But I would have to say the guys have really sharpened their tools and finding out models. And even we have Jerry Newsom still works on this project and have a time of his life. So, it's a really fantastic opportunity.
Yeah, Siddhartha Krishnamurthy, Applied Acoustics Branch. This may be a question more for Peter, but how different, or could you remind me how different the boom shape of the X-59 will be compared to the X-18 on its low boom dive? how different will the shape be? Like, will it be considerably different? I'm sorry, I misspoke. The F-18. Yeah.
So the F-18, when it would do a dive, would have a low amplitude N wave. So like Don was just talking about, it still had an N wave, but it was a lower amplitude because of the way the dive was performed. But in our airplane, we're not only going to have a lower amplitude, but we're shaping that so it's more sinusoidal in nature, so that the rise time to that pressure differential is slower and less impactful. That's kind of the short answer to that. But the F-18 was a great tool to do low amplitude booms, to do community response. You know, how do we do community response surveys? How do we survey people? How do we do the tools? So at Galveston, we learned an awful lot using that F-18, even though it wasn't the perfect answer. Okay. You got another one?
Yeah. Could you comment on the low frequency that are there any low frequency energy coming from this aircraft, meaning below hearing, like below 20 or 10 hertz?
See, he really knows what he's asking here now. So you're asking. So he is asking really good questions. Am I running out of time?
No, you can answer.
Let me do this.
You can answer that one.
Get this one.
question.
So we did a lot of work and a lot of studies and simulators on the ground, but this airplane essentially does have frequency content that goes along with it. So its length of the airplane and other factors do impact that frequency content. So if you're an acoustics guy, you're down around 10 or 30 hertz, you want to be able to have that low frequency content that simulates that commercial product that does window rattle and all those things. So you do want that energy. And so early on, we did look at what kind of size of airplane and weight and so on in order to, so we look like that commercial product. We don't physically look like it, but the sonic boom signature is close enough where we'll get that relevant data that we need for that frequency content you're talking about, right? Down 10, 20, 30 hertz. Below maybe some of your hearing. It's more of a feeling than hearing it. Peter almost can't take it. I know he wants to answer, right?
Less than 10.
Less than 10. Okay. You want to know what a Joshua tree looks like and you've never been out of the desert? There you go. Those are trees out there. And hopefully I can graduate to the Alumni Association here and be in good standing. Yeah, that's right. Thank you.